All right. Hello, everyone, and welcome back to the first talk of 2024 at the Temporal Graph Reading Group. We are excited to have you back, and for today, we are very excited to have Patrick and Alex discussing their recent work called Intensity Profile Projection, a framework for continuous time representation for dynamic graphs. And just a bit of an intro for our speakers today. So Patrick obtained his PhD in statistics at Imperial College London in 2008 and supervised by Prof. Andrew Walden. And he was awarded a Heilbronn Research Fellowship in Data Science in 2012, which he first held at the University of Bristol and then at the University of Oxford. He then became the assistant professor of statistics at the University of Bristol in July 2017 and was promoted to full professor in July 2022. As of January 2024, he is the chair of statistical learning at the University of Edinburgh, and his research interests include data exploration, graph embedding, and unsupervised learning. And Alex is the research associate in statistics at Imperial College London, and his research is in statistical modeling and large-scale inference for high-dimensional and graph-structured data, with a particular interest in unsupervised learning with temporal data. He is currently funded by the EPSRC grant called Network Time Series and Stochastic Processes. And I will hand the mic to you both.
Well, thank you very much, Andy. It's a pleasure to be here, or virtually, and we're delighted to present this work. We've agreed actually that we're going to try to not take too long here, just because we really just want to share the work and also sort of hear your thoughts, possibly collaborate, any questions, and as I said to Andy earlier, we take the questions at the end if you want, but also we're just happy to be interrupted whenever you want. The talk's not that long.
Sounds good.
Let me see if this works. What's going on? Right. Oh, just a little bit about how we're going to do it. So I'm going to start, and I'll just give you try to explain the problem in very broad lines, and give you a little bit of background, including our various pieces of progress that we had before this work, including what we perhaps think now of as the first version of our algorithm. And then Alex will take over and just tell you more about the V2, basically the algorithm that we're proposing now, a much improved algorithm for dynamic network embedding, and also tell you a little bit about directions we could go. So I thought it would be a cool idea to just jump straight into some data. Right. So what we're going to look at here is a data set. It's quite an old data set in a way. So in the 2009, volunteers were basically asked to put badges on, and this is in a school. And the badges had the property that if you come close to another pupil or a teacher, then it sort of pings and an interaction event gets recorded. So we have these data over 2 days about school children and their teachers, and we think about basically as a dynamic network, because what we have is all of these interaction events, which we think of as edges occurring over time. So a few sort of statistics about the data. There's about 80,000 events in total. So these are IJT triples, about 250 individuals. When I looked at the paper, I was surprised how many physical contacts there actually are per child per day. I didn't realize people mingled so much at school. And then a nice part about this data set is that we have labels, right? So if you're a teacher, we know you're a teacher, and if you're a pupil, we know you're a pupil. And also, if you're a pupil, we know which class you belong to, right? So which year. And for example, year one has there are 2 classes, 1A and 1B. Right? So we have these labels, and we can use that to validate some of our methodology. Okay, so that's a little network depiction of what's happening. So we just picked a few snapshots and you get a little bit of an idea of the sorts of connections that are occurring. The colors here represent different classrooms. And the problem of dynamic network embedding, in a nutshell, is to somehow try to find a good, in inverted commas, representation of these nodes, or well, actually of these nodes over time. So a little bit more specifically, if for each node at each point in time, we want some d-dimensional vector that somehow represents that node's behavior at that point in time. So if we let sort of t run over the 2 days that we're observing these data, then we can think about each individual here as a trajectory over space. So if we just run our algorithm, don't worry too much about how it works, because Alex will tell you more later. And we just zoom in to its performance in various senses, and this is a picture we get. So in what ways have I zoomed in, right? First of all, I'm looking at day 1 only, where we actually have 2 days. Secondly, I'm only looking at classes 1A and 1B. And thirdly, my trajectories, they're 30-dimensional, but I want to plot them, so I apply PCA. But I already need the x-axis for time, so I've only got 1 dimension here to play with. So I'm doing PCA from 30 to 1 dimension, and I'm just showing you the result. So what you see, so the colors here indicate the different classes, and what I hope to sort of convince you of is a few nice features, right? So the first, perhaps obvious thing is, you know, the algorithm doesn't know which pupil belongs to which class, and nonetheless we see a nice separation of the trajectories corresponding to class 1A and corresponding to class 1B. That's the first sort of sanity check. The second point, of course, is that the trajectories, they sort of come together at lunchtime, right? And that makes sense, because we know actually from the paper that all the school children were having lunch in the same hall. So they should actually all be having loads of contact at that time. And then the third point, which is perhaps a little bit less obvious and a little bit less sort of clear-cut in other methods, is that when lunch finishes, the trajectories go back to their original position. So we're not just seeing, you know, communities converging and then diverging. We really are literally seeing people going back to the same physical classroom that they were going to before, right? And in 30 dimensions, this would be completely clear-cut. Right, so there are 3 features here of our algorithm that, you know, might not have been completely obvious. Okay, so Andy, you mentioned this. We're really interested in collaborating in all sorts of different ways. I mentioned the NEST program grant here because it is a vehicle potentially for facilitating that. Right? So it's a large grant, as we call them in the UK, which involves various universities. Alex is a postdoc on this grant at Imperial. I'm a principal investigator, previously at Bristol, now at Edinburgh. If you like what you see, then we can work together, right? We have funds to bring you here. We have funds to visit you. We're recruiting postdocs, loads of things. So you go to the website and keep abreast of any of the events and any of the outputs of this work. And if you're interested, then please just get in touch.
That's very cool. Thanks for sharing.
So the broad themes that are covered by NEST in this sort of space of dynamic network embedding, well, maybe you could categorize them like this. You could talk about the internet, people and money, the planet, and the brain, right? So some of these application areas, we've actually got quite a long-term sort of programming. Some of these other applications, it's just a little bit more nascent. So in particular, in terms of computer networks and cybersecurity, we've been doing that for a few years. So we have, you know, quite a lot of papers. A little bit later, I'll talk to you about fraud and corruption, and I work with Microsoft, so we've been doing that for a while. One of the industrial supporters for the grant was the Royal Mail, so basically the largest postal service in the UK. And they're interested in looking at the dynamic network of their logistics, right? And what they want to do basically is try to reduce air travel. And actually, a lot of our collaborators have developed a lot of the ideas actually originally come from a number of collaborators who were interested in neuroscience and the study of the brain for different purposes. So these are the sorts of applications that have inspired us, and that perhaps we have in mind when we're developing methodology, but we're really, really open. If you have an application and you want to somehow put it to us and work together and figure it out, you know, we're really open-minded. You know, if it's interesting and it's fun, then let's just do it. And here's the address if you want to know more about what's in the NEST program grant. Okay, so high-level explanation here. You know, why embedding? And actually, I sort of realized first I should have said, what is an embedding, right? And in a very general sort of ML statistics context, what we mean by embedding, I think, is somehow a low or moderate dimensional vector representation of some complex object. So something like a node, the node, you know, the node in a graph, words, queries, documents. And when you dig a little bit deeper, you sort of realize that there are two important differences. Well, there's a dichotomy somehow in how people want to use embeddings, right? And it could be sort of put like this, right? Sometimes you're doing embedding for human purposes, right? Things like data exploration, visualization, helping scientists develop hypotheses, and then generally supporting this broader area of discovery science. I mean, other reason you might be doing embedding is for machine learning, right? So we kind of know that the easiest way to run a machine learning algorithm is to have a feature vector, right? So embeddings are ways of turning your complex objects into feature vectors, and that can help classification and regression, for example, help data fusion, help retrieval, and obviously it's fundamental to, you know, modern generative AI. And I just make this distinction because I think it's important when you think about what you want from your embedding and what makes a good embedding, right? So you might ask, for example, what sort of dimension should your embedding be, right? Well, probably if it's for human consumption, it should be relatively low, right? Whereas machines can handle slightly higher dimensional objects, right? If a scientist is using your stuff, it really helps if they can understand what algorithm is doing, right? So you need it to be kind of explainable, and you might want to sacrifice a bit of performance. And then, depending on when you're doing something like classification versus just clustering or some sort of diagnosis of global structure, you might prefer to achieve local fidelity, or maybe you really need global fidelity, and that trade-off will also sort of guide which sort of embedding you should be looking at. Right? So there's quite a lot of questions involved in what makes a good embedding. Okay, so just to give you a slightly more advanced application of embeddings that we engaged in about a year ago. So this is something we did with Microsoft Research over 2021 and 2022. I'll give you a little bit of breadth as well of how general purpose these algorithms could be. We were interested in anti-corruption, basically. We looked at Brazil because, as it happens, they had some of the cleanest data about their corporate contracting. So that was a data set we were able to sort of access. It's publicly available. And you can see that if you just looked at the data without sort of thinking in network sort of ways, right, it might not even be obvious that it's a network, right? I mean, it really is just a list of contracts that are sort of linking buyers, tenders, items, partners, etc. But of course, you can think of these as graphs. And in fact, you can think of these as graphs that are evolving over time, so dynamic networks. And in that engagement, what we were interested in is using embedding to help people somehow understand the data and find evidence of corruption. So you can look up the results of that work at this link here. But just to show you examples of how embeddings might be used here, there are different sorts of corruption that people are interested in detecting. One of them is bid rigging, so that's a bunch of companies that all sort of pretend to be competing against each other, but they're actually not. And in terms of embeddings, what you'd expect is those companies to sort of all be close to each other at that point in time. And then the other sort of corruption that they were sort of interested in detecting is when a company gets sanctioned or gets told basically that they have to shut down. Well, what they often do is they sort of reinvent themselves, come up with a new name, and suddenly do exactly what they were doing before, right? And in that situation, what you might hope to see in an embedding is that this company earlier was here, and this new company is very close, and somehow you can tell that it's the same company. Okay, so it always, I think it's always good to start with something really, really obvious and sort of understand why that isn't enough for your goals, right? And the most obvious thing you could do if you were trying to do graph embedding, right, is I think the following, right? You take snapshots of your dynamic networks and get T graphs, and you just use any technique you want to embed these graphs, right? And you just embed these graphs completely separately. So you use spectral embedding you want, you use node divide wherever you want. And you might ask, well, you know, what's wrong with that? There are two issues. I think one of them is not too important, which is the first one, which is, well, how do you get these snapshots, right? When you started with continuous time data, did you do some sort of binning here? How did you choose your bin? But the second issue is really kind of significant, right? Which is that you shouldn't really hope for any sort of coherence over time, right? So if you take the data set I was just showing you a second ago, and you just do separate embedding, you've got all of these sort of snapshots. So each snapshot corresponds to an hour of data, so a graph kind of representing that hour. And you see that basically it's just rotating all over the place. There's just no way of sort of making sense of any of the temporal patterns here. Right? So it'd be fine if you were just interested in a particular hour and you wanted to know what was going on, but it's not at all good if you're trying to get some sort of temporal picture about what's going on.
Just a quick question. How would you define coherence?
Well,
in your
that
case?
is a very well-timed question, Andy, because it's coming up right now.
Okay, great, excellent.
So in answer to Andy's question, what do we mean by coherence? So it's an opinion, okay? Like, I mean, there's no sort of mathematical proof here that this is somehow what you want, right? But it's an opinion that we have in this group that somehow your dynamic network embedding method should really try to guarantee two things, which we think are really kind of fundamental to most sort of sensible inference tasks that you'd want to undertake. The first one is what we call structural coherence. So we've just taken this description from the literature. And that's basically saying, if you look at a point in time and you've got two nodes that statistically are behaving the same way, then they really should be positioned in the same place in embedding space, up to some noise, right? Otherwise, it's really not obvious what your embedding is even trying to do, right? And then the second sort of coherence we think is really fundamental is temporal coherence. So if you have, if the same node at time 1 is behaving as it is at time 10, then we'd like its position at times 1 and 10 to be the same up to noise. And that's what we mean by temporal coherence. And really, if you've got a dynamic network method, then you know it's a very reasonable requirement, I think, to hope that some aspect of those two sorts of coherences would be guaranteed. So our first attempt at getting both of those sorts of coherences was what we called unfolded adjacency spectral embedding. So the word unfolding comes from the tensor decomposition literature. Technically, what we're doing is we're actually constructing a specific unfolding of the tensor representation of its dynamic network. But if you don't want to worry about tensors, then all you're doing is you're taking the adjacency matrices and you're sort of concatenating them one after the other, sort of side by side. And you just think of that as a big rectangular matrix. And then you do the SVD of that, basically, and you end up with the right-hand side of that SVD gives you positions for every node, every point in time. And after a rather enormous amount of complicated mathematical analysis, we were able to establish that both sorts of coherence were actually guaranteed. So it's a very simple example that's simulated here. You've got at time 1, so you've only got 2 time points. At time 1, you've got 3 communities. The green community doesn't change between time 1 and time 2, whereas the yellow and the blue community merge at time 2. So there are 2 things to check here. First of all, you do want those 2 things to be separate at time 1 and merged at time 2, so you can see that. And the second thing you want to check is that the green cluster doesn't move from time 1 to time 2. And in fact, it's a little bit of a detail perhaps, but we didn't just establish that the centers were the same. We actually established that the whole shapes were the same, right? So this shape here, theoretically, is identical to this shape, right? And so this was our first method that we came up with that was able to guarantee these two sorts of coherences, and we were very excited about that. And that's the method actually that we used for all of this work with Microsoft. And if you want to know about this sort of early attempt that we now call sort of version 1, then it's in a NeurIPS paper published in 2021. So just going back to the data, if you use unfolded adjacency spectrum embedding, then you can see that you've got a much better sort of temporal consistency, right? You've still got that structural coherency at every point in time, but you've also got the temporal coherency as well. So you can make a narrative somehow about what different classrooms are doing at different points in time. How am I doing here? Because I don't want to eat into your...
I think you're in about 20 minutes.
Okay, let's, last slide, okay, great. So V2, which is what Alex is about to describe, in a nutshell, is about going from snapshots to continuous time. Now, putting in a nutshell like that might make it seem like quite a small jump, but really, we're very excited about the amount of opportunities that suddenly arise, right? Because basically, the problem with unfolded spectral embedding is twofold. The first thing is, right, that, all right, in a dynamic network, it's probably better to think about each edge as a point process, right? So if I take a pair of individuals, I really want to be thinking about the sequence of times at which interactions happened. Of course, that sequence could just be empty. There might be no interactions. But if there are interactions, I really want to think about the precise timings of those interactions, because that opens the entire field, right, of point process modeling. You can talk about periodicity, you can talk about seasonality, change points, trend, and then sort of models or modeling approaches like the Hotz processes, Bayesian inference approaches. There's plenty of deep learning approaches now to like point process modeling. So you've got this whole space, right, of possibilities of point process modeling that unfolded adjacency spectral embedding just doesn't really allow. So that's the first thing that we really thought was kind of important to somehow extend to. I mean, the second part is a little bit more mathematical, right? But if you've got continuous time data, then you would want continuous time embeddings. And if you've got trajectories that are actually occurring in continuous time, then there's a lot of new mathematical notions that you can bring to the problem, right? So you can talk about continuity, and for practical purposes, you might be more interested in detecting discontinuities, right? That's only a sensible notion if you've got a notion of continuity in the first place. You can talk about topology, you can talk about smoothness, you can talk about derivatives. For example, one of the hot areas right now is kind of understanding network polarization. So this idea of communities forming and really sort of not even talking to each other anymore. This is something you could start to try to measure, right? By, formally as a divergence of velocities of the embeddings, right? And that's not a concept you even have access to if all you had was discrete time. Okay, pass on to Alex now.
Okay. Okay, thanks for the invite, Andy. It's a pleasure to be here. So I'm going to talk about this version 2 of our algorithm, which is called the intensity profile projection, which was published in NeurIPS this year. And so I'll start by just kind of describing the setup that we have here, kind of formally. So we assume that we observe an interaction network, which is we have a set of n nodes or vertices and a set of interactions. So an interaction is just an IJT triple, where I and J are the nodes and T is the time. And then just for notation here, we're going to have this EIJ denote the set of interaction times between nodes I and J. We're also going to make a kind of a modeling assumption that the interactions between nodes I and J are driven by some statistical model. And we're going to assume that that's parameterized by what we're calling an intensity, which is this lambda ij, which is parameterized by time t. So for example, this could be an inhomogeneous Poisson process, and then your lambda ij is the time-varying intensity of that process. And then an objective, like Patrick has spoken about, is to obtain continually evolving representations of the nodes, which meaningfully capture the evolution of the behavior of the nodes of the network, and which satisfy the guarantees of structural and temporal coherence that Patrick's spoken about already. So I'm just going to describe the algorithm now. It's quite simple. It's really just 3 steps. The first step is intensity estimation. So for every pair of nodes, we compute an intensity estimate, which we call lambda hat ij, of the lambda ij's. So if we assume that the point processes are driven by inhomogeneous Poisson processes, this could be a histogram, or it could be a kernel density estimate, or technically a kernel intensity estimate. So these are going to be potentially smooth functions of time. And then the second step of the algorithm is a subspace learning step. So before I kind of go into explain that, I'll just kind of describe what the notation we're looking at is here. So the bold lambda hat matrix is a matrix which is an n by n matrix, and its ij entry is the intensity estimate of the point process between nodes I and j at time t. So that's one big matrix which is evolving in time. And then we have the sigma hat matrix, which is essentially up to scaling, right, the average of lambda hat squared over time. So if we consider that the rows of the matrix lambda are data points, and we're going to call these, the rows of this lambda hat matrix, the intensity profiles, one intensity profile per node, and that's evolving with time. Then if we kind of look at this sigma hat matrix and we ignore the integral for a second, this looks kind of like a covariance matrix, because lambda hat is symmetric. And so what we can kind of view sigma hat as is a kind of average covariance matrix over time. And then what we're going to do is compute the top d eigenvectors of this matrix sigma hat. The third step then is to get the representation of node I at time t, we take our intensity profile and we project it onto the subspace spanned by the top d eigenvectors that we computed in the previous step. So fundamentally, you can view this sort of like PCA, right? We're learning a projection, and then we're projecting our data, a linear projection, and then we're projecting our data down into d dimensions using that. So I kind of mentioned this, but at its core, our algorithm is really quite simply intensity estimation. You can use essentially whichever intensity estimation method you like, and then dimension reduction. So, and this is kind of something essentially like PCA. So one instance of our algorithm could really fundamentally be described as a KDE, a kernel density estimate plus PCA. Or formally, I say kernel density estimate, I mean a kind of unnormalized kernel density estimate, right? Because we're estimating intensities. So the rest of the talk is going to be split into roughly 5 points. The first 2 are methodological. I'm going to talk about structural and temporal coherence, and in a bit more detail, with specifically related to our algorithm. And I'm going to show some simulated and real data examples which exemplify that. I'm going to talk in the second part about a fast approximate computation of the subspace that I mentioned. And then points 3 and 4 are the kind of theoretical aspects of this paper. The third point is showing that the subspace that we're learning is actually minimizing a notion of reconstruction error. And the fourth point I'll talk about is actually the bulk of the work in this paper, except for the methodological, except for the algorithm itself, which is the statistical estimation theory, which shows a kind of bias variance trade-off in how much smoothing we do in our intensity estimation step. And then point 5 is going to be really an invitation to you all. And I'm going to talk a bit about what is version 3. If this is version 2, what does version 3 look like? Hopefully it can involve working with some of you. So I'll get started with structural and temporal coherence. So this slide says exactly the same as what Patrick's did, except for I have a bit of mathematical notation here. So when I say structural coherence, I mean that if lambda hat I at t is an n-dimensional vector describing the intensities of the point process between node I and every other node in the graph, if they're equal for two nodes at the same point in time, then stochastically the embeddings that I obtain at both those times for both those nodes should be the same. So they should have the same distribution. And then by temporal coherence, I mean that if for a single node, if its intensity vector at time s is the same as its intensity vector at time t, then its embedding at each of those times should be the same, up to some statistical noise. And one of the lemmas in the paper is to say that intensity profile projection is both structurally and temporally coherent. But really, this isn't anything particularly complicated. It really is just simply a consequence of the fact that the embedding of node I at time t is just a fixed function of its intensity profile vector.
Just a quick clarification question before we go more deeper into the math. So I see this D notation floating everywhere. How do you actually pick the size of D?
So
how do you truncate the matrix?
The D here is actually saying equal in distribution.
Okay.
It maybe is bad notation. This is a different D to the embedding dimension.
Okay.
But for the embedding dimension, I mean, it depends on your task, right? Patrick mentioned that there's kind of two views of embedding, right? There's embedding for humans and there's embedding for machines. And if you're embedding for a machine, then often you have a task at hand and you can use something like cross-validation or whatever. If you have a supervised task, there's often a standard way to choose that with cross-validation or something similar. If you're doing embedding for humans, then the dimension really depends on what it is that you are trying to learn about your data. Right? You need enough dimensions that you capture the interesting structure in your data, but not too many that is not interpretable by a human. So really, I mean, it's task dependent, but
right.
It's a choice. And there's not. I think in our work we've kind of been doing this for quite a while, and we've realized there's not really a good way to answer that question. There's often not very good for just unsupervised tasks. There's not really a good way to choose it. It's just trial and error, really, I think.
Do you have some, do you think there will be some correlation per se about, let's say I said, for this task, I select like D equals to 10, and then I can also choose D equal to 9, and then these two embeddings should be like the structural coherence and temporal coherence. Maybe they will have some similarity, like they are just, one dimension difference. Is there some like bound or correlation between the two in a sense?
Well, so the problem, I mean, however you choose your dimension with this method, you'll have temporal coherence, right? However you choose your dimension.
Mm-hmm.
Problem is, if you choose your dimension too low and you throw away signal, then there's a chance that you will throw away some of the local structural information in your data. So yeah, I mean, really, I mean, we find kind of a lot of the time you'll kind of choose a dimension and look at the plots, and something doesn't, and then you choose a dimension a bit higher, and then you start to capture more information, and then you choose it even higher, and you stop capturing anything interesting.
I see.
Exploratory analysis. Yeah, I mean, so the problem is often it's fine to choose it a bit too high, but if you choose it too low, you can start to throw away important information, and then you potentially can't guarantee things like local structural coherence.
Okay, sounds good.
Okay.
Thanks.
Thanks for the question, Andy. So I've got some simulated examples here. So this is a simulated example where the edges are driven by inhomogeneous clustering processes, and my lambda matrix is block structured. So essentially there's two communities. They're initially behaving in a manner which is distinct. Then over time, their behavior gradually merges. So in the middle of these plots, they're statistically, all of the nodes are statistically indistinguishable. And then as time goes on, they start to diverge again, and they diverge back to the behaviors they started with. So what we should observe is if we have structural coherence, then the two embedding trajectories of the two communities should be initially distinct, come exactly together, and then return to their original positions. So if we have structural coherence, they'll come together in the middle, and if we have temporal coherence, they'll go back to the positions that they started in. So the top left plot here is our algorithm, intensity profile projection, where we've used a kernel smoother, or like a KDE, to estimate the intensities, and you see exactly that structure, right? That they're initially distinct, they come together in the middle, and then they go back to where they started. The second plot, plot B, is our method using a histogram estimator. And then if we look at some of the competing methods, the only other continuous time method we found was the plot E. And you'll see that the communities don't actually come together in the middle, even though they're stochastically indistinguishable in the middle. The embedding doesn't capture the fact that their behaviors have merged. So that's one. That method is not structurally coherent. Another method, if we look at C, which is doing spectral embedding, but we're actually trying to align each time point with the previous one to have some attempt at removing these rotations. We find that the red community and the blue community are distinct. They come together, but when they're we look at any time point, we see that they've come together, except when we look over time, they're rotating all over the place. And then when they diverge again, they've swapped places, essentially. So the aligned spectral embedding is structurally coherent. Locally, at every time point, they're either apart if they should be or together if they should be, but not temporally coherent. Over time, I can't look at the red community and say, is it behaving in the same way as it was before? And really, from what we've seen, our method is the only continuous time embedding method which satisfies these two basic guarantees. So that's simulated data. Now I'm just going to move on to real data. So this is the same data that Patrick described, but I'm just showing you a few more days here. So this is, what we've done is these are 30-dimensional embeddings, but we've looked at just two classes at a time, one per year, and done PCA to project each one down to 1 dimension. And then each line is just the average of the embedding trajectory of all the students in that class's embeddings. Because I mean, if we drew all the points, it would just be a bit of a mess here. So one of the things if we're doing exploratory analysis and we want to understand, well, just from these interaction data, what's kind of the structure of the school day, you can see that most of these classes are merging during the lunch hours, which is between 12 and 2. But there's also some other interesting structure that wasn't present in the study. We didn't learn this from the paper of the study, but actually we see that classes 3A and 3B seem to come together at about 9:30 on the second day, and they have some merging behavior at about 4 o'clock. So that could be potentially a joint class or a joint break time, for instance. And you see a bit similar behavior on the first day for classes 5A and 5B. So we're really pulling out some interesting structure, which from an exploratory perspective, tells us something really interesting about the data that we couldn't have found by looking at the list of interactions, for example. So I'm just going to now pull up, I have an animation, which kind of makes this a little clearer. So, I mean, when you have to plot things on paper, I can only use 1 dimension, but now I have a computer and time, I can do 2 dimensions and show you an animation and show you what every pupil looks like in this embedding. So if I run this, you see that they're initially distinct, and then, oh, actually, this is not the one I was going to run. Let me, this is the one I wanted to run. This is the one where classes merge at about 9:30, and they merge at the lunch break as well, and at 4. So we see this in the embedding. They're initially distinct, then they merge at that point, then they go back to their classrooms. This is the lunch hour where some of the students are mingling. They go back to their classrooms, and then we see later on another session of merging, which might be a break time, and then back to their classrooms. So this is a really powerful tool for exploring these complex temporal network data. Okay, I'm a little bit short on time, so I might have to rush through some of the rest of it, but I'll try and make sure I hit the key details. So the second point is what I was going to talk about is methodological. It's actually, if we look at the matrix which we're computing the eigenvectors of, it's actually a dense matrix, and there's this integral, right? So it's not really, we can't work with an integral on a computer, and we don't like to compute the eigenvectors of large dense matrices. But if we approximate this integral with a sum, we see that actually we can factorize the approximated sigma hat matrix. We can factorize it as this matrix here, which is this unfolding matrix, which is then, this matrix here equals this matrix times that matrix transpose. So essentially, what we have is that the left singular vectors of this matrix are equal to the eigenvectors of this matrix. And if our intensity estimates are sparse, so have lots of zeros in them, then this step of computing these singular vectors just reduced to a single sparse truncated SVD, right? And this is hugely scalable. We can go to tens of millions of nodes, potentially millions of edges, quickly on your laptop. So point 3 is moving on to the theoretical side. We might kind of alluded to the fact that this sigma hat matrix looks a bit like a covariance matrix, but it might not have been clear, exactly why I was why I was learning this projection. Why was I computing the eigenvectors of this specific matrix? Well, if I define this loss function, which I'm calling the integrated residual sum of squares loss function, which describes the reconstruction. So for any node I at time t, this r hat I t describes the reconstruction error of if I project the intensity profile vector down into d dimensions and then embed it back into the original space, what's my reconstruction error? And if I sum over all the nodes and integrate over all of time, then we find that actually the reason I've chosen to take the eigenvectors of this sigma hat matrix are because they exactly minimize this integrated residual sum of squares reconstruction error. So in some sense, given the intensity profiles, it's the best linear map I can use for my embedding. Point 4 is statistical estimation theory. Now, this really was like a big mathematical undertaking. And so this kind of took up the bulk of the time in actually producing this work. So I'll just give you the setup. We're going to assume that all of the point processes are inhomogeneous quantum processes, and that we're using a histogram estimator with m bins, sound intensity estimator. So, in practice, we like to use something more complicated, like a kernel smoother. But for the theory, using a histogram makes things independent and nice to work with. So it still gives us, an idea of how this algorithm performs in practice. So I need to define some population quantities. So these xi at t is the vector is the intensity vector projected down onto the population subspace. So I don't have a lot of time to describe the theoretical results, so I'll kind of go over this quickly. Basically, the xi's are the thing that we're trying to estimate. And this subspace coherence parameter is a parameter which basically describes how hard the problem is. So then one of the corollaries of the paper is to say that if our intensities are all of the same order of magnitude, they're Lipschitz constant with some constant L, and the sigma matrix has some nice properties. It's exactly low rank, it's incoherent, which means the problem is basically easy-ish. And we don't choose the bin size is too small. Then we have this high probability estimation error bound. And fundamentally, I mean, if you want to see the details, I'd recommend looking at the paper because I don't have the time to describe it here. But fundamentally, there's two terms. The first term is a bias term, and the second term is a variance term. And you can see that m is on the denominator of the first term and the numerator of the second term. So to optimize this term, we want to choose the bin size to balance the two terms. And it kind of makes sense, right, that L0 is how smooth the function is. And if L0 is larger, then we're going to need more bins, basically, to balance this bias variance trade-off. And in the paper, there is a more complicated bound with more parameters, which relaxes all the assumptions I've put up here. So we don't actually need to assume that the intensities are of comparable order. Sigma doesn't have to be of low rank, or it doesn't have to be incoherent, but you get a slightly more complicated bound. So finally, I want to come on to an invitation to you all, right? So this is version 2 of our algorithm, but what's next, right? What are the ways? What does version 3 of this algorithm look like? So I'll just kind of remind you. I'm just bringing it up here to remind you again of what it looks like. We've got and what could change, right? We have the intensity estimation step first, and then we learn a map, and we project the intensity profiles into the low-dimensional space using this map. Right, so this is this kind of similar slide to, again, fundamentally our algorithm is intensity estimation plus dimension reduction. So the work has established a really simple and flexible framework for obtaining continuous time representations of the nodes of a dynamic network, which are structurally and temporally coherent, which is really important. But we've only focused on kind of the simplest version of this algorithm. Right? We focus on simple intensity estimators, histograms, thermal intensity estimators, and simple dimension reduction tools, i.e. linear maps. But there are tons of opportunities to improve both the first and the second steps of this algorithm. And we invite your collaboration. So let's start with the intensity estimation. What could we do? Well, we don't need to assume that the interaction events are inhomogeneous Poisson processes. We can use all different methods from the literature, Hawkes process estimation, Bayesian methods. There's a big literature on using neural networks for temporal point process estimation. And these kind of methods can incorporate covariates on the events, dependence between point processes. Right, we just, in our algorithm, fit an independent estimate to each pair of nodes, to the point processes associated with each pair of nodes. We could relax this, we could do joint modeling. And we could hope to model different types of dynamic network data. Right, they don't have to be instantaneous interactions. We could hope to model persistent interactions, which have start and end times. We could hope that if our data, we observed heterogeneous observations of an underlying process, we could hope to model that. Basically, any model which is parameterized by an n by n symmetric matrix, right, which changes over time, and which we can estimate from our data, you can apply our algorithm. Right, so there are huge opportunities even for applications which don't have instantaneous point processes as the type of data. You can still apply our algorithm, right? And there are lots of different ways we could improve this and extend this intensity estimation step. The second point is the dimension reduction. So just to kind of recall what we've been looking at, the map that we use is a linear map, and it minimizes this integrated residual sum of squares criterion. But actually, we can view this minimizing this criterion as an autoencoder. So an autoencoder, right? You take your data, and you have some encoder which takes you into D dimensions, and some decoder which takes you back into your ambient space. And then if we replace our loss function here with the same loss function, but where we replace the linear maps with just a generic encoder and decoder, we can see that's the optimization problem for an autoencoder, but where instead of parameterizing the encoder and decoder with a neural network, I'm constraining them to be linear maps. But so you can see here, and with this view, we could generalize our algorithm to learn a nonlinear embedding function, which we learn using a neural network, rather than just learning linear maps. And this in particular is something I think that a lot of people in this group have experience with and would love to discuss these ideas with you and potentially work with you. So that summarizes everything I have to say. If you're interested in working with us or interested in this work or anything we do, you can contact either of us on these addresses, and these QR codes will take you to our websites as well. Thanks, Andy.
Great. Thanks for the great presentation. It's a very interesting talk, and thanks for digesting the complex math in a very readable and understandable format in such a short time. Is there any question from the audience? Feel free to type your question in the chat as well. And while we are waiting, so I'm curious so I think like all the future direction you mentioned is very interesting. And also you mentioned that we can do some sort of learnable embedding. So I suppose if you can extend the theorem and the coherence definition to GNN models applying on temporal graph, then maybe you can design GNN models with stability guarantee over time for temporal graph, would be helpful and then helps it to be more explainable, I guess. So then you can look at the embedding and say that, hey, these two nodes have similar embedding, so they should be, have the similar structure, or they are interacting in some specific way. You can maybe swap out the intensity function with a GNN, like temporal GNN, or something like that. So I just thought of that as a way. And also your definition currently is only applying for node level embeddings. So in some specific field, the edge, so defining if two edges are coherent, right? Because the edges are recurring over time. And technically you should treat them as separate entities. They might be the same edge, but doesn't mean that their function in the network is the same. If you look at the structural role they play in the network, like some edges could be acting as a bridge between two community at one point, and then now because the community have merged, so now it's just like within the same community, for example. So maybe some notion on the edge level, which could be a less like it's kind of similar to what you've done with the node, but on the edge level, and then people can really pinpoint, let's say, fraud detection or some sort of application on the edge level. And then what's most interesting to me, I think this notion of coherence you have can be extended to the graph level. So I work a lot on graph embeddings and for dynamic graphs like change point detection. So and then like sometimes it's just not feasible to generate node embedding and track it over time for like very large data sets, right? So you want to get some idea about how much does my graph stay the same? Like let's say you have a critical system where you have network traffic and you want to say, hey, am my system under some attack? So is this maybe breaking the temporal coherence? Then I can say, okay, within this much error or like this much attack range or edges that shouldn't be there, then this will report it as incoherent. And then in a sense, you kind of have an anomaly score kind of thing. So there's like many interesting directions. Yeah, and also like I'm very happy to discuss more in a separate meeting, or if you have time, like after this talk, I'm happy to chat more, like I have like 30 minutes afterwards to discuss more on this. Okay. So thanks everyone for coming to the meeting.